Hey, folks. Okay. Um, so Kepler's laws are, as I said in the video, a little convoluted, right? So it takes some time to break down what's going on, and if we do that, if we sort of understand, especially how ellipses work, then it makes understanding the motion of the planets a lot easier. So, first and foremost, right, if we're looking at Kepler's three laws of planetary motion, right? The first law is that the orbits of the planets are ellipses with the sun at one of the two focus points. So the focus points on an ellipse are always sort of in the corners over here, and for this ellipse, then the other one would be over here. Right? And so the major axis, right? The major axis is the longest diameter across the ellipse. So this whole thing here is the major axis. And then half of that from the center out to the long edge is the semi-major axis. Right? The center is the center, right? The intersection between the major axis and the minor axis. The perihelion, right? If the sun is here, the perihelion is the point in the orbit where the planet is closest to the sun. The aphelion is the point in the orbit where the planet is farthest from the sun. And then, well, as I said, the sun is at one of the two foci. Right? Foci is the plural for focus. Right. Right. So the first law is that every planet's orbit is an ellipse, specifically with the sun at one of the two foci. Right? The second law is that if a planet sweeps out the same area between two sections of the orbit, then those two sections must have been traversed in the same amount of time, right? So that's a little convoluted, right? But basically you're saying, okay, if the planet takes the same amount of time to go from A to B as it takes to go from C to D, right? If these two distances are covered by the planet in the same amount of time, then these two wedges will have been swept out in the same amount of time. Or say, those two areas, the areas of those two wedges will be the same. So, during which of these two sections of the orbit did the planet travel faster? Between A and B or between C and D? Well, between A and B, the planet traveled this distance. And between C and D, the planet traveled this longer distance. Right? How can the planet have traveled a greater distance in the same amount of time? Well, it must have been going faster. Right? That's the most important thing to remember about Kepler's second law, is that if these two wedges have the same area, then they were made in the same amount of time. Right? The distance traveled by the planet is going to change, but the time required is the same. Right? So, which section was traveled? Time between... so which of those distances was covered in a longer period of time? Between A and B or between C and D? No, they got to be the same. So if the planet went this distance in a certain amount of time, and the planet went this distance in the same amount of time, the only way that the planet can travel a longer path in the same amount of time is if it's going faster. So that's the general behavior, is that when a planet is closer to the sun, it's going to be going faster. When a planet is farther from the sun, it's orbiting with a slower velocity. Let's see. Yeah. So the planet, so then the planet moves fastest when it is closest to the sun. When is it closest to the sun? When it's at perihelion. That's the definition of perihelion. Okay, so here we've got that Kepler's third law is that the mass of the star, the semi-major axis, A, and the orbital period, P, are related to each other like this. What is the semi-major axis? Well, like we sketched out earlier, right? The semi-major axis is just half of the major axis, this distance here, right? But that's not the important thing. The important thing is that the semi-major axis is the same as the average orbital distance, or the orbital radius, on average, right? Sometimes the planet is closer to the sun, sometimes the planet is farther from the sun at aphelion, but the semi-major axis is the average distance between the planet and the sun, averaged over one orbit. So basically, the mass of the star, the orbital distance, and the time, right? What is the period of an orbit? The period is the time that the planet requires to orbit the sun one time. They're related to each other like this. Or, you can... Usually it's written like this because then you don't need to write a fraction or something. But all of these equations, these are all just different versions of the same equation, right? You're just solving the algebra. You're just solving the algebra to solve for A, P, or M, right? If you know any two, right? This is a three-part formula. If you know any two, you can solve for the third one. So if you know the mass and the orbital radius, you can solve for period. If you know mass and period, you can solve for semi-major axis, etc., etc. So, how shall we do this then? Oops. We can lay this out the same way that it does in the... don't need that. We can lay it out the same way that we did here, right? So let's say, okay, so here's the mass, here's the semi-major axis, here's the period, and if the mass is 1.00 and the semi-major axis is 1.52 astronomical units, then the period is what? Well, solve the equation for period, and you get that the period is the square root of a cubed over m. So then here, that's what? That's equals the square root. In a spreadsheet, you can just say square root, SQRT, square root of a cubed, so a cubed over mass. There we go. So that planet has a period of 1.87 years. All right, remember, the equation for Kepler's third law is laid out so that the mass of the star is always in solar masses, the semi-major axis is always in astronomical units, and the period is always in years. Okay? So this planet here, this is basically Mars, right? Mars is orbiting a one solar mass star, the sun. Mars has an orbital distance of 1.5 AU, and therefore Mars orbits the sun in 1.87 years. So almost 2 years. Okay. If we do this, 3.56, and we say, okay, so you got a planet, you've discovered a planet, let's say. What kind of scenario are we talking about here? Well, you're saying, okay, let's say we've discovered a planet. That planet is orbiting around a 1.75 solar mass star. And then you discover that planet orbits its star every 3.56 years. Well, how far away must the planet be from its star? What is the distance between that star and that planet orbiting around it? Well, here's our solution for the semi-major axis. If you're solving for A, right, you just take the cube root of both sides and you say, okay, then A is the cube root of MP squared. And it's a handy shortcut. It's a handy shortcut to remember that in general in algebra, if you have the nth root of x, right? If you're taking, the square root, the cube root, the fourth root, whatever, the nth root of x is just the same as x to the 1 over n power. So a square root, right? A square root is just x to the 1/2 power. A cube root of x is just x to the 1/3 power. So that's what we're doing here, is saying, rather than find the cube root button on your calculator, because I am lazy and can't be bothered, right? So then I'm just going to put in mp squared to the 0.333 power, because 0.333 is the same thing as 1/3. X to the 1/3 power is the same as the cube root, which is what we want. Right? So that's what we're doing here, is to say, this is just a shortcut, right? In your calculator or in your spreadsheet, it's easier to just raise something to the exponent of 0.3333 rather than hunt around on your calculator trying to find the cube root button. It's just easier. So, okay. So then here, A equals what? Equals M. Oh, nope. Open parenthesis, right? M times the period squared, right? So we got all that, and then raise it to the 1/3 power. So, to the power of 0.333333. Okay, there we go. So then, this planet you just discovered, this exoplanet, this alien world orbiting around a 1.75 solar mass star, it orbits its star every 3.5 years. That planet must orbit 1.8 AU from its star. Okay. And now the last one, 0.75 AU. So that planet is orbiting pretty, closer to its star than Earth is to the sun, right? It's only orbiting its star in three-fourths, right? 7.75 AU, with a period of 2.14 years. What must the mass of that star be such that it is pulling its planet into orbit around it at this distance in this amount of time? All right, well then the mass is a cubed over p squared. So then the mass of this star equals a cubed over p squared. All right, that must be a 0.09 solar mass star. That's a pretty low mass star, right? Which makes sense, because if you're a planet orbiting closer to that star than the Earth is to the sun, and yet despite the fact that you're closer to the star, it still takes you 2 years to orbit that star one time. Like, that star must be so low mass. The gravitational pull of that star must be so weak that even though you're pretty close to it, it still takes 2 years to go around it. Right? So that tells you something about how strong the gravitational force is. The gravity of that star is not strong enough to pull that planet around any faster in a shorter amount of time. How can the gravitational pull of that star be so weak? Well, it must be lower mass. So that makes sense. Alrighty. So let's try some of these practice problems here. We'll go back here. In the diagram below, the time between each planet's position shown is exactly 1 month. So it takes a month to go from point to point. Where is perihelion? Well, perihelion is the point closest to the star, so that must be perihelion. Where is aphelion? Aphelion must be over here. I'll put peri just to make it clear for myself. Between which 2 points is the planet moving fastest? Well, if we know that the planet moves from point to point in the same amount of time, then the planet must be moving fastest when it covers the greatest distance in that amount of time, and the greatest distance, or the fastest velocity, and the greatest distance covered is going to be around perihelion, when the planet is closest to the sun. So between M and A must be when the planet's moving fastest. At which dot is the planet moving slowest? Well, if the planet is moving faster when it's closer to the sun, it must be moving slower when it's farther from the sun. So it's moving slowest at aphelion, which is labeled G. What is happening to the planet's speed between B and C? Okay, so I didn't say explicitly, but if we're going in alphabetical order, which was what I was going for, right? Then the planet must be orbiting the star counterclockwise, right? So the planet's going around like this. So between B and C, the planet is moving away from the star, and if the planet is moving away from the star, if it's moving from perihelion to aphelion, then the planet must be slowing down. So its speed is decreasing. When the planet goes from H to I, now the planet has passed aphelion, it is now falling back toward the star, so from H to I, the planet is going from aphelion to perihelion, it's going from slowest to fastest, the planet must be speeding up. Right? The speed of a planet is constantly changing, slowing down for half the year and then speeding, well, I should say half the year, slowing down for half the orbit and then speeding up for the other half of the orbit. The velocity changes depending on the distance. Faster when it's close to the sun, slower when it's farther from the sun. Okay, so now we've got some similar problems to the ones we just solved, and since we already have our spreadsheet to do the work for us, then we should be able to make quick work of this. All right, so this first problem here, you're orbiting a 1 solar mass star like the sun, but you're orbiting at a distance of 5.45 AU. That's basically Jupiter, right? Jupiter is orbiting a 1 solar mass star, the sun. Jupiter has an orbital distance of 5 AU, so then the orbital period of Jupiter must be about 12 years. Makes sense. But now, what if, we got the second one here, right? What if you're orbiting a 2 solar mass star at the same distance? Well, if the planet is the same distance to the star, but the star is more massive, then the gravitational pull of the star pulling on the planet is going to be stronger, and if that star is pulling with a stronger gravitational force, that's going to make the planet go faster, and therefore it should orbit in less time. So we would intuitively think, like, okay, if the star is more massive, the planet should have a shorter orbital period. It takes less time to go around the star once. So if the sun were 2 solar masses, Jupiter would only take 9 years to go around the sun. All right. Here we got the second option here, where you're orbiting around an 11 solar mass star, an 11.4 solar mass star. That's a pretty darn massive star. Okay. And you're orbiting in 2 years. So that's a pretty high mass star. But even though the star is high mass, it's still taking 3 years to orbit it once. So that planet must be pretty far away, right? You would sort of intuitively think, if you're sort of waving your hands and, thinking about it, you're like, all right, this star is pulling on that planet with a really strong gravity, and yet the planet still takes 3 years to go around the star once. If the planet takes 3 years, it must be really far from the star, such that it takes 3 years to travel this longer path, this longer orbit. So, all right, 4.5 AU away. All right, makes sense. And what if you are orbiting 0.426 AU? So you're orbiting pretty close to the star, and it takes 0.34 years, so it takes less than a year. So you're orbiting closer to the planet. The planet's orbiting closer to the star, and it doesn't take much time to go around. So that makes perfectly good sense. So that sounds like a scenario that's pretty close to our solar system, right? In our solar system, if a planet has an orbit, if it's closer to the sun than 1 AU, then it should take less than a year to go around. And so this sounds like something close to our solar system. So if you were making a guess as to what the answer should look like, looking at these numbers, you're like, all right, this kind of sounds like our solar system. I'm guessing that this star is probably similar to the sun. And okay, it's a little less than the sun. It's a little less than the mass of the sun, but pretty close. So, all right. That makes a bit of sense. All right. So now that you got the spreadsheet laid out with all the equations you need, all you got to do is input your new measurements and it'll give you all your answers. So you can add this table to your spreadsheet, and I like to sometimes highlight, like, okay, here are the things that I can enter, right? Highlight the cells that I can change, and then you could highlight these in a different color if you wanted to or something, but maybe, I don't know. Color code it any way you want to. Make the cells one color for the ones that you can change, and then highlight a different color for the cells that you don't want to change because they've already got the equation programmed in, and you don't want to change the equation. You just want to change the inputs to figure out the answer to your calculation. So, I'll sometimes do that for my spreadsheet, is just do some color coding to say, okay, you can change the yellow ones, but don't change the orange ones, because the orange ones are where the answer comes out. But that's just a nice reminder to yourself. That way you don't accidentally type a number in here and then erase your formula, because that's annoying. You spent the time writing the formula. Of course, if you accidentally do that, all you got to do is, undo, Control Z, and you've saved your formula. So, okay. All right. I hope that's making a bit of sense. Getting a handle for Kepler's laws certainly helps us understand how anything orbits anything, right? Kepler was trying to figure out how the planets orbit the sun, but now we know better, right? Now we know that why do the planets orbit the sun? Because of how gravity works. And gravity works the same everywhere in the universe. And so anything orbiting anything will orbit according to Kepler's laws of planetary motion, quote unquote. And therefore you can use these equations, you can use Kepler's 3 laws, and you can use these formulas to figure out the mass, the distance, and the period for anything orbiting anything. Moons orbiting planets, planets orbiting stars, asteroids orbiting stars, satellites orbiting planets, 2 stars orbiting around each other. A star orbiting a black hole, a star orbiting the center of the galaxy. Anything orbiting anything will do it according to Kepler's laws, because that's how gravity works. And so these calculations are good for planets and also anything else that is orbiting. So this is a pretty powerful tool for figuring out what's going on out there in the galaxy, without having to rewrite your equations. So, all right. I hope that makes some sense. And if you got questions, post them to the discussion board. Until then, have a good one.